So what did we do last time? We sort of, okay, so last time was really the Convex MPC lecture. We did this whole like convex optimization overview, which was the very, very accelerated crash course in kind of like what is convex optimization. If you're into this stuff in general, I would highly recommend taking a convex optimization course, a full course in this at some point in your life. There's several offered at CMU in like multiple departments, so worth checking out. If you want to self-study, highly recommend Stephen Boyd's CVX 101 course, which is like online on YouTube and all this kind of stuff. And the book is online. Can somebody go close the door back there, actually? That'd be super helpful. Thanks. And then, so we did the kind of overview about convex optimization, and then we did Convex MPC, right? And this is super useful, and it's sort of the workhorse of modern control, I would say. It's like probably the go-to move when you like come at a new problem. And then today, I wanted to just offer a little like couple little extra, kind of examples of Convex MPC stuff, which we'll talk about later in the course, but just to kind of finish that discussion a little bit from last time. And then we're going to get into nonlinear stuff, right? So we did this whole convex thing. If it's convex, by definition, the dynamics have to be linear. You're only allowed to use linear dynamics. So now we're going to kind of get into the nonlinear story, which will take a while. But so we're going to do nonlinear trajectory optimization, kind of intro today. And we're going to spend a decent amount of time on this. And so intro, and then we're going to get into one particular class of algorithms for solving nonlinear trajectory optimization problems, which is called differential dynamic programming. And there's sort of, yeah, we'll talk about this. There's sort of two broad categories of algorithms for solving nonlinear trajectory problems, and this is one of the big. This would be like, so there are two broad classes. This would be the most popular and most representative of one of the two classes. So we'll talk about this, and then next week we'll talk about the other broad class, which are sort of collocation or direct methods. So that'll be the next couple of weeks. Any questions about anything? All right. As usual, yell at me if you have questions, because I will be distracted and not looking at stuff. Okay, so some kind of quick other MPC examples, just to finish off from last time. So last time we really mostly talked about actuator limits, right? Just like box constraints on your controls, which are super useful for torque limits and all kinds of other things, like thrust limits on your quad rotor is one we did at the end last time. There's some other examples though that are, so last time we talked about different kinds of convex problems. We talked about QPs in particular being like a really popular kind of setup. But we also talked about cones being convex, right? And it turns out cones are actually pretty widespread in the control world. So I'm going to show you a couple examples of where cones come into interesting, fun problems. First one is rocket landing. So this is the so-called rocket soft landing problem, or powered descent problem, depending on which version you're doing. And this is what SpaceX does to land the Falcon 9 on barges, and everyone's seen this, and it's awesome. It's also how JPL lands rovers on Mars, the power descent stuff for Mars. Also how Astrobotic up the street here is hopefully going to land on the moon soon, this whole story. So here's how this works. So the main hard part there is generally, actually, maybe very surprisingly, you can get away with modeling your spaceship as a point mass. It turns out, like in a lot of cases, or what actually happens in practice is you decouple the attitude dynamics from the position dynamics. This is also common on quad rotors, by the way, if anyone's looked at quad rotor controllers. So you do the same thing on a rocket, it turns out, in practice. Like, this is usually how it's done. And the reason you can do that is that the attitude dynamics tend to be unstable and fast, whereas the position dynamics are a lot slower. So you have a fast attitude tracking loop, and then you have a slower position loop. And the MPC is done on the slower position loop. And that's what we're going to talk about right now. And so where this shows up is that, so you use point mass dynamics actually, but the thrust vector that your rocket can produce is constrained, and it very naturally is actually a cone. And so we'll draw this real quick. So you can imagine, you have a rocket. You have your nozzle down here, smoke and fire comes out. But the way it works, right, you have a throttle, so you can adjust the magnitude of the thrust, and then you have a gimbal on the rocket motor that can steer the rocket nozzle around, and usually within, I don't know, plus minus 10, 15 degrees, something like that, right? So you have those two actuation things. So this guy can do this. And so if you think about this, this is naturally a cone where you have the height of the cone is your thrust limit. And then the sort of angle of the cone here is your gimbal limit, which is how far over you can tilt the rocket nozzle. So that's a second order cone problem. This is like the standard approach to this problem. Actually, the fact that you could set this up this way was a huge deal about 10 years ago. And this was invented about 10 years ago by this was a major paper by these guys, Lars Blackmore, who now runs the GNC group at SpaceX, and Betchett at Chickasha, who's a professor at the University of Washington now. It's like a huge deal. It's one of the major control results of the last 10 years. It's super cool. And yeah, Mars landing, SpaceX rockets, it's super cool. So this is second order cone program based MPC with linearized dynamics. There's more details that I'm glossing over, but we're actually going to spend later in the course, we're going to do a bunch of case studies on cool, state-of-the-art modern control things in practice. And this is one of the ones. So we're going to spend actually more or less a full lecture on this, going through how it's done and all the tricks, because it's cool. So stay tuned, or you can go read the papers, which are fun also. Okay, so that's one. And another one where the conic stuff shows up are legged robots. So the place it shows up there are in, it also shows up in driving, actually. Contact forces with the ground. You get, someone just said it, friction cone, right? So let's draw that. So when you have, let's say, your foot on the ground or your tire in contact with the road, same kind of thing. These forces, so you have your normal force, and then you have your tangential force or friction force, right? And it turns out these are constrained. And the constraint is called the friction cone. And this looks like, if I call my friction or tangential force B, this guy's 2 norm has to be less than or equal to our friction coefficient, which is called mu, which is a scalar, times the normal force. So this is friction force, which is a vector in R2. And then this is friction coefficient, which is a scalar. And then this is normal force, which is, again, a scalar. So if you want to draw this, kind of the picture is that you've got the ground. And then, if my foot's there, I have my normal force kind of in this direction. And the cone deal is basically, I can only have as much friction as mu times this guy. And this is actually, you've probably seen this friction coefficient mu kind of idea from high school physics. This is the legit 3D version of that. So that's friction cones. These show up a lot of places anytime you have contact tires, feet, actually grasping and manipulation as well. And the other kind of like aside here, so this was, if you were to do this, the legit way, you would just throw it in there, second order cone problem, cool, go. It turns out that in legged robots in particular, there's a trick that people often play, which in my opinion is kind of unnecessary, but it's standard to actually approximate this cone as a pyramid. So you make like, 4 flat sides. The reason is if you approximate it as a pyramid, then the constraints are linear and you can write it as a QP instead of an SOCP. And for kind of like mostly historical reasons of like, SOCP solvers are a little newer and generally not quite as fast, although it's changing. People preferred using QP solvers because the solvers were better and there were better like fast embedded solvers for solving QPs. So that's kind of, if you look into this stuff, you'll see this friction pyramid approximation. And this is okay if your goal is to just not slip. If you're trying to be conservative, then it's okay. But if you actually need to reason about slipping, like if you're trying to do drifting in a car, for example, this friction pyramid thing is like not good. It's going to be very inaccurate. So you don't want to do it if you actually need to, if part of your system's operation involves sliding contact, this is bad. If you're just trying to put this on as a conservative inner approximation and say, don't slip, then it's fine. Anyway, standard thing you'll see. We'll talk more about this when we talk about legged robots. So yeah, what this looks like is I have my cone. And I would like, say, do this. Inside, so it's like a conservative inner approximation. This is this setup is basically what the MIT Cheetah controller does, and that sort of now everybody basically copied that. So like the standard quadruped controllers on all the quadrupeds you see running around are basically doing this. They're doing QP based in MPC with this friction pyramid approximation for the friction on the feet. Okay, let's see.
Does this also extend to...
Yeah, bipeds are a lot harder though. So in the humanoid biped world, people play the same kinds of games. But you'll notice like quadrupeds are almost like a solved problem now, and you can just buy them. Humanoids, bipeds, not so much, right? Like you don't see those running around everywhere. And there's good reasons for that. So maybe we shouldn't go too long on this and get distracted, but the gist of it is so I told you like they're using a QP, like Convex MPC controller in this, right? So there's obviously a ton of approximations there to get it to be linear. The big one is the MPC controller is just reasoning about the body as a single rigid body and ignoring the leg dynamics. And they can get away with this because on most of these quadrupeds, they put all the motors in the body and the legs are super lightweight. So unlike Cheetah and most of these other quadrupeds, the legs combined are only like 10% of the total robot mass. So you can safely ignore the like inertial effects of the legs, and the controller is basically just reasoning about the body dynamics and like assuming it could just put the legs wherever it wants, like super fast. So on a quadruped, you could do that. On a humanoid, the legs are way beefier and heavier and tend to have the actuators down in the legs. So they have a lot of inertia relative to the body. And you can't get away with that approximation. So this standard kind of QP situation where you can get away with like these linear single body dynamics kind of break down in the humanoid case. And the humanoid control problem is much harder because you can't play these games. Yeah.
But there are also like humanoids kind of like standing upright and quadruped now, like they're using very similar and like Cheetah design. So wouldn't that change the game?
Yeah, so this is a longer conversation. Probably we can talk about this out. I don't want to get too distracted, but yeah. So you can use similar techniques, but getting it to look like a QP involves a lot of approximations. Those approximations are pretty good for a quadruped where all the mass is concentrated in the body and the legs are approximated as massless. It's not a very good approximation for like Atlas, right? Where the legs are much, much heavier. And so you have to do different things. Yeah, you can, and that would make this work better. And that's actually many of the quadrupeds that were designed over the last 10 years the hardware design was made with light legs, partly to make these approximations in the controller work better. So yeah, there's like definitely some like, you know, kind of controller informed hardware design going on in this stuff. You're totally right. Yeah. Okay.
For the friction point.
Yeah.
In the last lecture, you mentioned about X2 to N, right? So what is X2 to N?
Oh, I was talking about the, like if you have an n dimensional X, you take, so in this case, yeah, so here specifically, if you made the full contact force vector, friction and normal force, it would be a 3D vector, and N would be, you know, the first element, and B would be the 2 and 3 elements, right? So B is, you know, X2 to N, and N is X1, in like what we talked about before. Does that make sense?
Yeah.
Cool. Yeah. So if that was, hopefully that makes it more clear. Okay, so that's sort of teaser stuff about linear MPC, convex MPC, right, that we talked about before. And just as a kind of quick finishing up sort of discussion that will lead into the next topic, what about nonlinear dynamics, right? So all this is about linear dynamics. So just some thoughts from me on this. Basically, like the first thing to say is that linear models are surprisingly effective for smooth dynamics. You can get really far with linear models. And so it's always worth a shot. Like when you're coming at a new problem, it's the first thing you should try. You should try to linearize it about a set point, you know, and or a trajectory, and see if you can get away with a linear controller. Because it generally works. It works surprisingly well. It's like very effective. So you should try it first. That's sort of thought number one. There's actually a funny line. This guy, Art Bryson, whose name will come up maybe, who wrote an early book on like control theory, who's a professor at Stanford for years and years. Like in his book, he had this little like quip, be wise, linearize, like about like nonlinear control, and that you should probably just do the linear stuff most of the time. So yeah, if you can use it, the linear stuff, do it. So specifically with regard to MPC, like why do we spend so much time on this convex thing? Well, as soon as you add the nonlinear dynamics into that MPC problem, it becomes non-convex. And it's just much harder to solve. Like at a first pass, how do we solve the nonlinear problem? We do Newton's method, where we end up linearizing and solving these Newton problems. So just right out the gate, as soon as you go nonlinear, you're going to have to solve more Newton iterations, right? By relinear. So it's more expensive. And then on top of that, now that it's non-convex, you might have spurious local optima, and you can't guarantee super robust convergence of these solvers at real-time rates to like global optima and stuff like this. So there's both this issue of it's computationally harder, and then also you're going to give up a bunch of these nice theoretical guarantees about optimality and convergence rate and all this kind of stuff that you have in the convex setting. So those are kind of the big downsides to the nonlinear stuff. That said, there are plenty of, you know, just straight up, the world is nonlinear and non-convex, and there are lots of hard control problems where you have to do this, right? And so when we get to those situations, in practice, we just do it. And you can make it work, but it takes like the convex stuff, there's all these guarantees and it will work. Whereas in the nonlinear setting, it can often take a lot more engineering effort to tweak your problem setup, Monte Carlo the thing, play with the solver, and to get it to be reliable. And still, you know, in theory, it could fail, which is scary if it's like a safety critical application. That said, you know, in some of the most safety critical applications, people are doing this. So in particular, in autonomous driving, the standard like car models that people use are nonlinear, and they're doing nonlinear MPC on these cars. So, you know, take what you will from that. You know, if you're talking about Tesla, they're, you know, they take some risks, but like pretty much all the autonomous driving stacks do nonlinear MPC. So it is done, but you have to be extra careful. And generally in those stacks, what they do is they have the nonlinear MPC thing, and then they have some dumber fallback safety controller if the MPC solver barfs online. So you might want to think about that if you're doing nonlinear things in a safety critical context. Yeah, effort, what else? Yeah, that's basically the story. There are scary demons lurking in there, but you can do it. We do it, it can be made to work. Okay, any questions about that stuff?
So there's a difference between like suboptimal, right? Even though we don't get the optimal.
Yeah, so in a lot of cases, like in this nonlinear MPC thing, we live with suboptimal solutions. In fact, it's like impossible to know if you have the globally optimal solution, right? All you can check for is local optimality. So like best case, we're getting some local optimum, right? And yeah, generally we just don't care. As long as the robot, doesn't look stupid and face plant and kind of gets where we want to go, we're okay with that, even if it's suboptimal, right? Because ultimately, what is optimality? Like we're making up the cost function, right? Like, so we typically don't really care about strict optimality.
Even in that case, because if you live with suboptimal.
Yeah. That's right. Yeah. So in this kind of nonlinear MPC setting, like kind of the state of practice, I would say, is to approximate lots of things and live with feasibility and suboptimal feasible solutions, i.e. you're obeying the constraints, right? As long as you're obeying the constraints, like obeying friction limits, obeying torque limits, whatever actuator limits, and it's not falling over, it's generally you're willing to live with this as an engineer. And so that's kind of, yeah, it gets very sketchy and like there's a lot of hand wavy, stuff in there, but like this is why I say with effort, like it often involves a lot of tuning and games, and yeah, we usually live with suboptimal solutions and we're okay with that. Cool. All right. So this concludes the MPC conversation for now, and we're going to switch gears. So speak up if you have any more MPC comments or thoughts. All right. So now we're going to get into the nonlinear trajectory optimization thing. So first, we're just going to go back to basics and write down the problem. So we wrote this down before as kind of this general optimal control problem. So I'm going to kind of restate it. We could talk about it a little bit. So we've got states, controls, and we've got a cost function, additive cost function over time. So k equals 1 to n minus 1. We have a generally non-convex cost. You can make this whatever you want. But in practice, I would say like 90+% of the time, we still use quadratic costs, even here, because they're like easy to work with and pretty intuitive to like, design behaviors with. And then we've got our dynamics, and these are general nonlinear dynamics now. And then we have general state and input constraints. So these could be, don't hit the obstacles, that kind of thing. That was a terrible math cal X. Let's try that. Yeah, not pretty. And then we've got, your actuator constraints, which again, here, general, anything you want can be non-convex. So let's like notes here. Cost, nonlinear dynamics. And then these guys, general non-convex constraints. Cool. And so we're going to assume here, it's pretty standard to assume, and like we will actually for the derivation we're about to do, we're going to assume that all the functions here, so like the F, the L's, and whatever these constraint sets are, like the functions that define them, we're going to assume that everything is at least C2 smooth. So meaning like well-defined up to second derivatives. because we're going to do Newton's method where we have to take two derivatives. So that is why we assume this, right? That said, in many cases, you can do things with less smoothness, and it's not a super big deal. As long as it's like differentiable at least once, you're generally okay. C2, which is means continuous second derivatives. Okay, cool. Any questions about that? We've seen this before, right? This is like the generic optimal. This is a basically the most generic, discrete time optimal control problem, right? Okay, so how do we solve this thing? I kind of mentioned, at the outset, there's like many ways to approach this. Today, we're going to talk about one approach that is kind of coming out of the LQR Riccati dynamic programming viewpoint, right? And so we've seen that whole derivation a couple of different ways. So we're going to sort of think about this is going to come out of that like LQR Riccati dynamic programming kind of line of ideas. And so let's see, how do we do this? So differential dynamic programming. And the way to think about this is it's approximate dynamic programming, which is very, very common in RL, right? Where you like throw a neural net in and do dynamic programming. Here, instead of throwing a neural net in to approximate the value function, we're going to use a Taylor expansion to approximate the value function. So it's really what ends up happening then, and then we do Newton's method on it. So it's really a mashup of dynamic programming with Newton's method. That's kind of the way to think about this. Let's see, that's what it's called. It's abbreviated as DDP. This algorithm, the ideas date back to the late 60s, but it's been reinvented at least a couple of times, including as late as like in the 2000s. It was reinvented again by somebody in robotics who renamed it ILQR and like didn't cite the original 60s papers. This bothers me to some degree. So like, I don't know, you should like know the history, and like it has been, there's at least like two independent like reinventions of this decades later. But the original paper is Maine from like 1967 or something. Okay, so let's see, what do we say about this? Nonlinear Trajopt method based on approximate dynamic programming. And it'll be clear where the approximate stuff is happening as we do this. This is terrible. And the gist is you're going to use a second order Taylor expansion of everything in the dynamic programming stuff we did before. So like the cost to go, right, et cetera, and then do Newton based on that. And so I think having said that, it should be all the stuff we're about to do should be fairly obvious based on that. Cool. So that's kind of the general algorithm idea. And then like the kind of takeaway, or like the thing about this and the reason this is popular, there are trade-offs between this and some of the other approaches to solving these problems. These things can have really, really fast convergence, which is cool. So they're sometimes favored for like embedded MPC applications because they can be super fast. And there's some reasons for that. One is that you're doing Newton steps, which have fast local convergence. And the other is that in these methods, you do an explicit rollout with the dynamics, which means you're always satisfying the dynamics, which is not true in some of the other methods. And so that combo means that you get really fast local convergence with these. Okay, cool. Any questions about the big picture? No, we're just going to do it. Okay, so yeah.
Like what I'm understanding is we use non-linear when we can't do linear, right? Like
yeah, like if you need to do something, if you have to, so like everything's nonlinear to some degree. And, sometimes you can get away with a linearized dynamics approximation, sometimes you can't. And then, so
So when you think you can't, like, is it like you can't approximate it, or it is like it's going to give that?
I mean, it's a continuum there, right? So like what's going to happen is you're always approximating it. Depending on what you do with the robot, that approximation will be better or worse, right? Like if I'm like, okay, quad rotor is a good example. If I linearize that thing about a hover and I fly relatively slowly, that linearized approximation is very good. If I now try to go do like a barrel roll, the linear approximation is going to break down. So like if tends to be if you are like, so like the linearization is a local approximation. So if you don't drive the system too far away from the point you linearized, it's really good and you'll do fine. If you need to do something where you have to move the system through a large region of state space and you can't like you're going far away from the linearization point, it's going to do bad, in terms of.
And we have new linearization point about like
Yeah, you can do lots of stuff like this, and we're going to talk about this more. But yeah, generally speaking, if you need to execute like aggressive behaviors that push the dynamics, like push the capabilities of the hardware, this tends to be where you're going to like not be able to get away with conservative linear approximations and stuff like this, right? Okay. This is a bit of an art, and there's no like hard and fast rules, right? So it's one of these like, you should probably try the linear stuff first. And if that's enough for what you care about, done. But if you're trying to do something kind of aggressive, high performance, or you just have a particularly nasty system that's super nonlinear and those approximations don't hold up well, then you've got to maybe think about this kind of stuff, right? Okay, cool. So let's get into it. So remember from kind of last time, this idea of cost to go function or value function from like the backward passive LQR. And this is going to look a lot like LQR. In fact, one of the names for this is iterative LQR. So that should be a hint at what's going to happen. So remember in LQR, we had this quadratic V, right? And we kind of back propagated it through the linear dynamics. Here, we're going to basically do the same thing. The one difference is that in LQR, we had only a purely quadratic V. Here, we're going to get a linear term and a quadratic term. And the idea there is in LQR, you're giving it a reference to track. So it's like you're basically forming a quadratic bowl around the reference. Here, we're trying to find an optimal trajectory. So you get a gradient term that's like pushing you downhill towards a more optimal trajectory, right? At convergence, the gradient term goes away and you just have the quadratic term and you recover the LQR kind of thing, right? We'll see that. But in general, you're going to carry around this extra linear term in the value function that we didn't have with LQR. So here's what this looks like. I'm going to like Taylor expand this value function. So I'm going to get a constant term, and then I'm going to get a linear term in the Taylor expansion, and we're going to use p, little p for the gradient. Sorry, this is delta x. So that's a linear Taylor expansion, right? First order Taylor expansion. We're going to do a second order Taylor expansion. So we're going to get the next term, which is 1/2 delta x transpose. We're going to use big P for the Hessian delta x. So this is the gradient. And then this guy's the Hessian. Cool. Second order Taylor expansion. Now what we're going to do is, remember from LQR, at time step n, at the final time, it's just the terminal cost, right? So in this case, it's if we have the like more general nonlinear L, nonlinear or non-convex cost function, these are going to be the gradient of the terminal cost and the Hessian of the terminal cost. So same deal, we just might actually have to compute these things. We might have to actually compute some derivatives to do these if it's not a straight up quadratic cost function like it was with LQR. But again, we typically use quadratic cost functions anyway, so you can just write these things down. Cool. Okay, so next move. So that's the time n. Now we're just going to do the backward Riccati sort of Bellman, whatever you want to call it, through time, going backwards. And we're specifically going to write this down. There's a few ways to write this down. I actually think this derivation is clearest and kind of cleanest using the action value function thing, or the Q function if you're RL. I'm not going to call it Q function because Q for LQR, but that. So I'll write that thing down. We're going to call it S, which we did before. And we're just going to do the same kind of stuff where we Taylor expand that thing. So let me write that down. So this thing is S sub K. And remember, this thing's a function of both the state and the control. So we're going to have to Taylor expand it in both X and U. And I'm going to write this out, same deal, second order Taylor expansion. So you get the constant term, you get the linear term, and I'm going to write this down. We're going to kind of write the X and U terms in here separately because we're going to use them. We're going to compute them sort of independently in a sec. And I'm going to use little g for the gradients here and big G for the Hessian in this Taylor approximation. So there's the linear term, and then here's the second order term, the Taylor expansion. This is going to be, I should move this over. Okay, and then this is, so we've got, we'll call it GXX, GXU, GUX, GUU. So I'm just like writing the blocks down, right, separately. So we can write this like blockwise. Cool. And then also, yeah, the Hessian's symmetric positive definite, or we want that to be true at least. So it's definitely symmetric. So in this case, we've got GUX equals GXU transpose for that thing to be symmetric. Okay, cool. So that's that action value thing. Now we're going to write down the Bellman equation, that like one step little optimization as we go backward. And just kind of plug and chug like we did with LQR. We just get a few extra terms associated with the gradient term and the linear term and the Taylor expansion now. So let's go back one step. So we're going to write Vn minus 1 of X is min over delta U. And we're going to just plug in that action value function Taylor expansion. So we've got S of XU plus G sub X transpose delta X, G sub U times delta U. Then we've got the quadratic stuff. So let's see, I'll write these on separate lines. So we've got this delta X, GXX term. We've got delta U, GUU. And then we've got the mixed terms. So delta X, GXU, delta U, and then delta U, GUX, delta X. Okay, so that's the whole thing. And now what I'm going to do is calculate just like we did with LQR. That's the whole thing. And I want the min with respect to delta U. This thing is a quadratic, positive definite thing. So I just take the gradient and set it equal to 0, just like with LQR. I've just got a bunch of extra terms now, right, to carry around. But otherwise, same idea. So we're just going to set grad with respect to U of this thing, which I will be lazy and write like this. So if I write this out, it's really easy. Check my math. Everyone cool with that? Didn't mess up, I don't think. And so, yeah, that bottom row, we can like basically combine those, right? And that's what the last term, the GUX term is. Cool. So just like LQR, we got this thing, that has to equal 0. And now I can solve for the feedback kind of thing by solving this thing for delta U as a function of delta X. So I now get, from here, I get delta U n minus 1. And the first part looks like minus GUU inverse times little gu. And then the second term we're going to get is GUU inverse GUX delta X. So the second term over here looks exactly like LQR, where we have a feedback term, where we got feedback on delta X, right? So this thing we're going to call K, just like in LQR. So this is Kn-1. But unlike LQR, we also get a feed forward term or constant term that doesn't depend on delta X. So this, and the feed forward term is coming from the linear term in the Taylor expansion that we didn't have before, right? That like gradient term. So we're going to call this guy Dn-1. So the whole thing then is we do this and we get a feed forward D and then a feedback K. And then okay, questions about that? So that's kind of the punchline of this part. So it looks very, very similar to LQR, but you get this new term that's coming from the linear / gradient term in the cost to go. That gives you this like feed forward correction on the trajectory, right? And we also get the feedback. Everyone cool with this? Questions? Yeah. That whole thing, yeah. Yeah, make. Does that help?
There should be an S10.
Oh yeah, sure. This is Sn-1 actually. Cool. Okay, so that's straightforward. I think it's fairly clean in terms of that action value function thing. So that's the one step. We get the correction on the U's, the delta U stuff. And then remember, we have to plug this back in to get Vn-1, right? So that's the next part. And this is pretty straightforward. It's just like, there's nothing deep here. I'm just doing like algebra, just subbing it back in, right? So don't plug delta U back into Sn-1 to get Vn-1 of X plus delta X to get this Taylor expansion. So if I go ahead and do that, I'm going to get Vn-1. This Taylor expansion is approximately constant plus. So this stuff, the G stuff, is already functions. Remember, all I'm trying to do here is plug in this U as a function of X stuff. So I get rid of the U's because I just want this value function has to be just a function of the X's, right? Okay, so there's an X term. The U term now. So this was GU times delta U. So I'm going to plug in the feedback or the solution to get rid of the U and make it just in terms of X. So now this is minus D n-1 minus K n-1 delta X. That's it. So I'm just going to, everywhere there was a delta U, I'm just going to plug that in, right? So no surprises. It's like just a bunch of algebra. So this doesn't change. And then the quadratic term in U, I just plug this in on both sides. So Dn-1, K n-1 delta X, GUU, same thing again. Then the mixed terms, we're going to get this kind of thing. Plug it in here. And then the other direction, mixed terms. Okay, that's the whole thing. So now what I do, just like when we did Riccati LQR stuff before, I'm going to take this, I'm going to massage it around, and I'm going to figure out what the P matrix is, like the big quadratic, P matrix up here, and the little p, so that then I've bootstrapped it and I have a recursion. I keep going, right? So that's it. So I'm just going to take this thing that I just wrote down, this big messy guy, and collect all the quadratic terms. And that's the new big P. Collect all the linear terms. That's the new little p, and write them together. So that's looks like this. So we get Pn minus 1 equals Gxx plus K transpose GUUK minus GXUK minus K transpose GUX. Cool. And then little p, similar deal, GX minus K transpose GU plus K transpose GUUD minus GXUD. So it's just like Riccati with like more bookkeeping for the linear terms, but like conceptually the same idea. Okay, this gets a box. All right, that's easy, just algebra. So now the last step of this, which is going to require a little detour because I'm going to teach you like the legit way to do it instead of hand waving through some tensor math that everyone else I think tends to hand wave. We'll do the real thing. So it's going to take a little bit. So need some more math. So, all right. So basically this is it. And the last step is how to calculate the big G and little g blocks from that action value function. So we're going to do that next. But at a high level, this is the whole algorithm, right? Like it's just like Riccati. You do this backward recursion and you kind of do a forward rollout. Okay, so now we do little detour through matrix calculus. So here we go. First off, any questions about any of this before I make a little, yeah.
How did we get the equation for the very long expansion for d of x plus delta x?
Yeah, so this is just here. So this is like the Bellman backward pass where I take like the one step cost and the value function for the next time step with the dynamics plugged in. Remember last time, like we actually just called that the action value function.
Right, I'm just saying, you're saying we get, okay, are we substituting back into that?
Yeah, so this thing right here,
Okay.
that's the definition. So I'm going to solve for delta U
And then plug it back in.
and plug it back into there
Okay,
to
I
get
was
rid of all
confused
the
'cause there's no delta U in
U's.
the initial approximation for d of x plus delta x.
Right, yeah, so that's because it's only a function of the state, right? But then when I do the backup and I have the one step with the controls for the one step in there, I get this guy.
Right,
I
so that
solve
gives
this for U for the one step, and then I plug the U back into that S. And once I've eliminated the U from the action value guy, it's just the value function again. Make sense? Cool. All right, so yeah. Those are feedback gains, just like the K matrices from LQR.
How do you determine it? You don't really know it in.
You get it just like, I mean, it's just the math. It's just that it has this structure. But literally, when I minimize this thing with respect to U, that's what the answer is. I solve for U. And it turns out that when I solve that equation for U, when I minimize it with respect to U, remember that thing, that action value thing is a function of both X and U. I minimize with respect to U, but it's still a function of X then. So that's why you get this feedback on X thing, because it's still a function of X.
So when you minimize with respect to U, you get the value function.
That's right, yeah. So if I have action value function, if I minimize action value function with respect to U, I've minimized out U, but it's still a function of X, and that is the value function. Yeah.
The
That-
function in general means optimal, right?
It's the optimal value function, cost to go function, whatever you want to call it. Yeah.
But for action value, there is nothing called optimal.
Oh, I mean, it is. So literally action value is just the optimal cost to go value function plus the one step stuff. It's literally the thing that shows up in the Bellman recursion. That's just by definition. I don't know. It's a thing in RL. It's like people made up a name for it, whatever. But it's literally just right. One step cost, value function for the next time step with the dynamics plugged in. That thing is this action value function. Probably should have written that out again.
I just what I wanted to ask, you update K for each step.
Yeah. So we're doing basically backward Riccati, calculating these Ks on the way back at each time step.
Did you have K updates? Not sure if I missed it. How do you update K? Is that something you know beforehand?
No, you're calculating it right now. So the way this overall algorithm works, we make a guess. Like this, we'll do the whole picture, but you make a guess at like the trajectory. You linearize around it, Taylor expand around it. Then you do a backward pass where you compute these Ks and Ds. Then you do a forward pass where you simulate a rollout with these Ks and Ds in it. And that gets you a new trajectory. That gets you right. You'll get a full new set of X's and U's in the rollout. And then you'll relinearize and do another backward. So you iterate these backward and forward passes. And those are basically the combo of backward forward gets you the Newton step. Yeah. Yes. So yeah, this big nasty mess right there, I literally just take that and group all the quadratic terms together and all the linear terms. So if I take all the quadratic terms, whatever matrix, when I say all the quadratic terms, I mean 1/2 X transpose bunch of stuff times X, right? Whatever the bunch of stuff is big P. Then when I group all the linear terms, I have bunch of stuff transpose times delta X. What do you mean? So I mean, it's by construction that we're computing a second order Taylor expansion. Like I decided I wanted a second order Taylor expansion. So like by definition, it's got a linear term and a quadratic term. I don't know. Yeah, like I decided to write down the second order Taylor expansion, right? So that's what it's got. It doesn't, yeah, nothing like, there's nothing magic about it. I just like decided that's what I was going to calculate. Yeah.
When you differentiate with respect to U, do you assume Sn minus 1 term to be constant with respect to?
No, Sn minus 1 is a quadratic function of X and U.
Then why doesn't it show up in the differential? Is it?
Here?
Yeah.
Yeah, so that thing is a function of delta X and delta U, right? Oh, maybe I should write down it's actually delta U that I'm differentiating respect to. Does that help? Sorry, I was like yeah, the delta thing is, I'm sometimes lazy about writing those and that might be confusing. Okay. Anything else on this? So I highly recommend, like the only way to really learn this stuff is just go do this yourself. Like the best way to do this is look at this, like kind of like internalize the like general idea, like the flow of the algorithm, whatever, and then like put it away for a couple days and sit down and try to drive this yourself without looking at the notes or whatever. That's like how you learn. Because honestly, there's like barely any ideas in here. It's really just like second order Taylor expansion of value function, do dynamic programming. That's it. Like I don't remember any of this stuff, but I can sit down and rederive it in 10 minutes when I need it. Like that's what you should do if you want to like really understand it. You got to understand how to like speak the language, right? So I just remember like, two things, like Newton's method, second order Taylor expansion, right? And dynamic programming. And then I can just write all this stuff out like in a few minutes. So like that's what you want to be doing, right? Like the little details in here don't really matter. That's just like basic vector matrix math, right? So if you know how to do the math, it's only a couple things that are actually the key ideas in here. And the rest of this is just mechanics, like turning the crank, right, on like the algebra. So yeah, don't get hung up on any of this. Like as long as you understand how to do matrix math, you should be able to do this yourself. And I would highly recommend, like, again, if you really want to learn it, you should be able to like crank through this derivation yourself, in 10 minutes or whatever. Just remembering like the couple key moves.
One question, like last time we worked with value function, now we are doing action. Why, how to know which will be?
It's totally arbitrary. I could have done this just with the value function and the dynamics and stuff. It's just cleaner this way in this particular, like I chose to write it out in terms of action value because we'll see in a minute. I'm going to expand it now and do it in terms of just the value function. It's much uglier. So it's just more ugly stuff to keep bookkeeping. It's happens to be cleaner right now. Yeah. It's totally like the action value function is like, I just made that up, right? Like it's literally just, I made up a name for the thing inside the Bellman backup equation.
But in that case, you must fix because it's all further
Use not fixed, like, so action value function is literally just, I take the value function for like time k plus 1, I plug in the dynamics and I write down the one-step cost. And the U shows up in the dynamics and the one-step cost. So that's the U, right? That U is not optimal or anything. That's just, it's before I optimized it, right? Once I like set this gradient equal to 0 and get this feedback thing, that's the optimal U. But that optimal U depends on X, right? And so once I plug that optimal U in and I eliminate the U and I get it just as if that's now the value function, right? Does that make sense? Yeah, I mean, it's just bookkeeping. Like I just decided to make a name for this and give it a letter because it makes this little cleaner, less bookkeeping, right? Okay, cool. Everyone okay? Okay, so here's a detour through matrix calculus. This is stuff that, like, I don't know, I didn't want to hand wave through. We could have easily skipped this, but I feel like this is stuff you're not going to learn anywhere else probably, and like you might as well know about it. So I don't know. Okay, so stuff about derivatives. How do I differentiate a matrix with respect to a vector? That kind of stuff, right? So it turns out we have to do that to get these things. So I'm just going to show you. Okay, so if I have f of x, we talked about this stuff, before, like basic gradient Jacobian kind of stuff. Let's take a look at this. So this is like, vector valued function of a vector. Let's look at the second order Taylor expansion of this guy. So specifically, right, we're thinking here about like the dynamics function is kind of where this is coming from. So if, let's say m equals 1, so i.e. this thing is a function of just a, it's a function of vector, but outputs a scalar. So think like cost function. Then this is easy. And I get x plus delta x equals, or is approximately constant plus partial f partial x times delta x, where this guy is 1 by n. And then the second order term is going to be, like our usual Hessian that we're used to. So 1/2 delta x transpose b squared f dx squared delta x. And this guy now is your Hessian that you're used to, and this is n by n. Okay, so that we're used to. That's what you do when you get a cost function. Well, let's say now that n is a vector, if n is greater than 1, like a vector, like as in this is a dynamics function. And look at what happens now. So if m greater than 1, and generally like we're talking about m equals n for dynamics, you've got f of x plus delta x. We've got constant term. We've got linear term, which if we're thinking about dynamics, this is your A matrix, right? This is your Jacobian. So this guy is m by n. And now what happens in this second order expansion, this quadratic term, I'm going to write it the sort of least terrible yet mathematically precise way I can without introducing a whole bunch of new notation right now. Then we're going to introduce new notation and ideas to actually do it. So the way to think about this, right, is I take the term, I take that first order term and I diff it again, right? That's what I'm writing here. And this is like sort of a different beast. This is kind of ugly. And if you're, there's a bunch of ways to like notate this kind of thing and think about it. And maybe the standard way would be to call that second derivative of f a third rank tensor. and write it down using like some kind of summation notation or whatever. So maybe a lot of you have seen this. Yeah. Where? No. No, yeah, it's inside because I wrote it in this weird way. So the way this thing is really in this setting where it's vector valued, like each vector spits out a vector. One derivative is a Jacobian matrix. The next derivative is a third rank tensor. You can think of this like a 3D matrix. Like we pick up another dimension in this thing every time we take a new derivative, right? So that's kind of weird. Who's done like tensors before? Handful of people, not too many. But okay, so does it make sense, like kind of what I'm talking about, though, if you haven't seen this before? Okay, so let me just write some notes here. For m greater than 1, this second derivative thing, so d squared f dx squared, is what's called a third rank tensor. And heuristically, like you can think of this as a 3D matrix. Or 3D array, you know, whatever. And basically, we're going to introduce, you can think about this like as a 3D thing and like write down like some index thing with 3 indices and like do a bunch of Einstein summation stuff. But you don't need to. So I'm going to show you the hacker engineer way to do this, which is both mathematically precise and plays nice with like MATLAB, Python, Julia, matrix math and stuff, and is a lot easier to do without having to invent a lot of new notation. So there's a couple of tricks. So the kind of the key issue is if it's a 3D matrix, if you're trying to compute like the equivalent of X transpose, QX or whatever, there's 3 options for which side to multiply on. So in 2D, you have like left and right. Now with this tensor, you have left, right, and like, I don't know, back or front kind of, right? There's different sides. There's a new side to multiply on. So like the gist of this is you have to keep track of which side you're multiplying your X on this third rank tensor. The physics convention is to write it down as like Qijk, where I and Jk are the indices corresponding to like the 3 sides. And then you just keep track of it that way, which is basically like writing out for loops over indices of a 3D array, but that's sort of annoying. So we'll show you another way. Okay, so some new ideas. The first idea is called the Kronecker product. I teased this when I was building these sparse matrices for the MPC stuff before. It's super useful. It's a good thing to know about. Who's seen the Kronecker product before? Knows what it is. Okay, most of you guys. Where have you seen this before? Curious. Poisson equation? Oh, interesting. Okay. Yeah, that makes sense. Okay, so here's what this thing is. So if I have 2 matrices, A and B, you write it like this. It's like circle with a X in the middle. And in like MATLAB, Julia, et cetera, this is called Kron, K-R-O-N. And the definition is you write out a few elements of this thing. You take each element of A, the matrix on the left, so each scalar element, and you multiply it by the entire matrix B. And then like you expand that out. So this is kind of what it looks like. And so if you have, say, so dimension-wise, this thing gets huge, right? So if this is L by M, and this is N by P, this thing is sort of the multiple, you multiply all of these dimensions together. Does that make sense? Cool. So that's trick number 1, Kronecker product. It's a standard thing, matrix math. It's in MATLAB and whatever. And then the other trick we need is called the vec, or vectorization operator. This also shows up in a few places. It shows up in control. It's actually one of the ways of solving the nonlinear Riccati equation, involves doing this. And so the idea is, if I have some matrix A, I'm going to take its, I'm going to write A as like this, where these are the columns. So if this is M columns, this guy is L by M. These are the column vectors. And so I'm going to define this thing called vec of A, and I'm just going to stack up all the columns from that matrix into one big column vector. Cool. Has anyone done this before? It's called vec in MATLAB and Julia. You can also do it in MATLAB by parentheses with just a colon. We'll do this. Okay, so then this guy is LM by 1. Okay, those two things is pretty much all you need. The gist of what we're going to do is basically like flatten matrices. Basically, all of these tricks involve like flattening the tensor into a 2D matrix so we can do regular matrix math. So this is kind of the idea, right? So if I kind of like take my matrix and like stack it up into a vector, now I can just take a regular Jacobian. And that's that Jacobian of this sort of stacked vec thing will actually be the flattened version of that 3D tensor flattened down into 2D. That's like what all these tricks are about. Okay, so you need one more piece of fun math. I don't know any other name for this, so I call it the vec trick. Here's what it is. If I have 3 matrices ABC, I can write down, so if these 3 guys multiplied together, assuming the dimensions line up, this is equal to C transpose cron A times vec B. And it turns out you can like, so like a corollary of this is I can make any of those the identity. So for example, I can do vec of AB equals B transpose cron I vec A, which is equal to also I cron A times vec of B. Why am I doing this? This is how I diff a matrix with respect to another matrix, or diff a matrix with respect to a vector. Okay, this is where we're going with this. Okay, so cool with that. This is easy to derive if you just think about these things like column or row wise. You can figure this out pretty easily. Like not hard. You can sit down and it's also on Wikipedia. I don't know what they call it though. But yeah, this is what I call it. Is that like I don't know. Everyone I know who does this calls it.
That's why Julia stores matrices in column major order.
No, that's just like an old school numerical thing. Like basically there's 2 camps. There's the column major and row major, and like C and C derived languages are column major and Fortran is row major. And like this was just someone who designed those languages in like the 50s and 60s made these decisions and they stuck forever.
So we're still pioneering SSV.
Yeah, exactly. There's no like legit reason for that. It's just random choices made by random people 70 years ago or whatever. Okay, so here's why this is useful to us. If we want to differentiate a matrix with respect to a vector, you just vectorize the matrix and go. And so where this shows up for us is in these tensor terms, the second derivative of the dynamics, like what we're basically doing is taking partial A, partial X, where A is our dynamics Jacobian, right? That's the stuff that shows up. So this is, you know, if I want to do this, if I have A of X, where A is my A matrix, and it's a function of the state X, I can do this. We're going to just, by convention, if I write this down, if I diff a matrix with respect to a vector, it implicitly means I'm doing this. So this is going to be Lm by n. And this is like the idea is we're this is implied. The vec is implied whenever I diff a matrix. So if you just kind of use that convention, whenever you see a matrix derivative like this, it turns out it all works out. Like if you just use this convention, apply this trick, the chain rule works, everything you're used to works, and you can just kind of keep trucking and do all your usual math stuff, and it works out. So if we now like go back to Taylor expansion of our dynamics, say, and apply this, we get f of x plus delta x, constant term, partial f, partial x times delta x. So this is the stuff we already know how to do. This is our A matrix from our dynamics, right? And then the next term that we're after is going to look like this. And I'll show you in a sec like how to get this thing. This is just me using the vec trick. And this is using this implicit vectorization inside this derivative. So that's it. This is a totally mathematically legit, expression for the second derivative term in the Taylor expansion using these tricks. So this works. You can code that up in Julia, MATLAB, whatever you like. And okay, so how do I get this? I take this guy and I write this down as partial respect to x of vec I A of x delta x. And then I use the vec trick where those are my ABC, right? And I get this guy, and then this guy here is partial vec of A partial x. Cool. That is it. This is all the tricks. This is how you can do tensor math the hacker engineer way in MATLAB or Julia. And it turns out you can pretty much do all of tensor math this way. It's like all of this weirdo stuff with like index notation. You don't really need it. You can just do this stuff and it works out and you get the same answers. And it's easier to code up too. Like you can code the stuff up in standard, MATLAB, Julia, whatever, like this. Okay, there's, I lied. There's one more trick that we need. Sometimes we also need to diff through a transpose. And to do that, we just make something up. So if I have the following thing, say like A transpose B, I can write that as B transpose cron I. And it would be here partial vec of A transpose partial x, right? So what I want to do is get rid of that transpose inside there. And so what I'm going to do is define this matrix called big T that applies the transposition to the vec of A, right? So it's basically going to reorder the vec of A such that it's the vec of A transpose. And it turns out you can just do this with a matrix. It's pretty easy to figure out what this should be. It's just like a permutation matrix. And we call this the commutator matrix. And so it's defined such that T vec of A equals vec of A transpose. Okay, that's it. You can figure out what it is if you want to. You can write it out. It's not like that big a deal. It's just a big permutation matrix that shuffles around the ordering of that stacked thing. Okay, that's the whole thing. We have 3 minutes left. So let's do, let's see how far we get. And then maybe I'll just we'll pick this up next time. Okay, so from there, we can go finish off our action value function derivatives. So we have this thing. So this goes back to what's the definition of this action value thing? It's one step cost plus value function for the next time step. with the dynamics plugged in. And I need to Taylor expand that whole thing to second order in X and U. So you can see now where the second order derivatives of F are going to show up if I second order Taylor expand that whole thing. So let's do the first order derivatives are easy. So we get partial S, partial X equals partial L, partial X plus just chain rule, partial V, partial X times partial F, partial X. And we know this guy is A. And so from there, I can this is my little g from all the stuff we read out before. So this is grad L plus A transpose P. If I transpose everything and use the other notation. So this, we'll put a box around this. This is the little g that we used. We can do the other one. So this is partial S, partial U. Same stuff. No surprises. This is B. And if I transpose this all around, I get GU is grad L respect to U plus B transpose P K plus 1. Okay, that gets a box. Okay.
That will be del B by del A.
Yeah. that's chain rule.
Oh, yeah. Sorry. You're right. Do that. Sure, that seems fine. Everyone happy with that? Okay, cool. And then you get the second derivatives, which I'm just going to write down. You can literally, it's just apply the tricks that we just talked about to these guys. Take another derivative of both of these. And here's what comes out. I'll write these down, and then we'll call it a day. So this is partial, this guy with respect to X again. And it turns out what you end up with is Hessian of cost with respect to X. And then you get a term that looks like this. And then you get the tensor term that looks like this. And then you get similar things for these other guys. So Hessian respect to U. And then the last one, which is this mixed thing. Okay. Okay, cool. That's the whole thing. This gets a box. Now you have all the ingredients. But we'll do the sort of final put it all together thing next time. So this is the whole thing. These, now you have all the G's, blah, blah, blah. You have the whole algorithm. So because we're kind of out of time, we'll start here next time and I'll show you the full algorithm, sketch it out, whatever. And we'll play around with it and do some fun things. Cool. So these are the so-called tensor terms. Well, that's weird. How did it do that? Okay. Cool. To be continued. There's a lot of algebra on this one. We're almost there though. There's literally just little outline. Should I tease the code part? The code part's fun. I'll tease you with the fun stuff, so you come back next time. Here's here's the finished. This is the punchline when I code this up. You guys know what an acrobat is? It's a double pendulum with one actuator at the elbow. And you can do this. If my code works.
So are we holding?
So no, this is just being really slow. There you go. So it starts down here and you like swing it up. Which is super fun. So this is like super nonlinear. You can't, right? So everyone knows like double pendulum is like chaos, super nonlinear. So it's one actuator, so it's under actuated. And yeah, it kind of like pumps energy in by doing like this double pump move.